This video lecture here contains a very short introduction to classical molecular dynamics. The aim in classical molecular dynamics is to study the time evolution of a chemical system, that is, to figure out how molecules move relative to one another. By the term classical here, we mean that the motion of the atoms are completely determined by classical mechanics, that is, by solving the Newton's second law. So we assume here that no quantum effects are important in order to describe the motion of these molecules. We can rewrite Newton's second law into a differential equation by substituting for the acceleration the second derivative of the position vector with respect to time. This is for particle I, the index here. And by substituting by the force on this particle here, the negative of the gradient of the potential energy in the system with respect also to the position vector of atom number I. Note here that this potential energy that enters into this Newton's second law here, in fact, is the potential energy calculated using a force field. So this is how a force field actually enters into molecular dynamics. Now, in order to solve this second order differential equation, we need two initial conditions. First, we need to know where are the particles at time equals 0. This is I0. And then we need to know what is the velocity of these particles at time equal 0, and this is the VI0. With these two initial conditions here, we can now solve this Newton's second equation here, and by this the positions and momenta of all the atoms at any time after t equals to 0 are completely determined. The way that we choose the initial configuration here can be different from system to system. We can, for example, use as an initial structure an X-ray structure if we have such one, or we can simply build our molecular system using a molecular builder. The initial velocities here are usually assigned to the molecules by assuming a Boltzmann distribution, so we assign these initial velocities here in accordance with the temperature of the system. And this is how the temperature actually enters into molecular dynamic simulation, so this will give rise to a kinetic energy. And this is different compared to molecular mechanics. So in molecular dynamics, what we do is that we study the time evolution of the system, and we have available thermal energy in our system, we have kinetic energy, and we have a temperature. In molecular mechanics, this is a static picture of the chemical system, and here we do not have any thermal energy and we do not have any temperature, or in other words, the temperature is equal to 0. It turns out to be extremely complicated to solve this differential equation here describing Newton's second law. So instead of relying on an analytical solution, what we do is that we solve the differential equation numerically. And we do this in the way here that using the settings for t equal to 0 at time equal to 0, what we do is that we compute the acceleration through the force on all the particles, and we can then predict where the particles should be placed at a very small time step ahead in time. Then we update our chemical system according to this very small time step, and what we do next is that we update the acceleration again through calculation of the force of all the particles, and we again predict what is the new position of the particles. So by this, instead of having the blue line here, which would represent the analytical solution to the system, what we do is that we have a discretization of this blue line here into small time steps delta t, where in each of these time steps here we recalculate the force on each atom in our system. Thereby we know the acceleration, and then we can use an updating scheme in order to predict what is the new position of the given atom. Now in the exercises we will look much more into detail in such a predicting scheme, or simply a scheme that we can use in order to integrate this differential equation here describing Newton's second law. And the specific method that we will be looking into is called the Verlet algorithm. So much more on this in the exercises. There are different ways of solving this second order differential equation, but note here that all the ways that we can solve it here should resolve in a total conservation of the energy. Although the kinetic and potential energies can fluctuate in the system, the total energy should of course be conserved. So this is a very important property to actually check using these different propagators. Now let us try here to describe the steps that we should go through in order to set up and to perform a molecular dynamics simulation of a chemical system. The first thing that we need to do is to look at the system representation. So this is that we need to define a way to describe the atoms. We need to define a way that we will account for the interactions between the atoms and so on. Then we need some simulation setup details. We need to choose from where should we get the initial configurations. Do we have any solvent around our core system? So do we have any boundary effects? Which time step should we choose in our simulation, and so on. After we have done this, then we need a heat up and equilibration phase of the simulation. And this is due to the fact that this initial configuration that we rely on here, well, usually this corresponds to a zero temperature configuration. And now we need to heat it up, so we need to put in energy into this system here until we achieve the desired temperature. And this is what we call the equilibration phase, where the system simply is not in equilibrium and where we have very large adjustments of the structure. Then after this equilibration phase here, we enter into the production phase, where we actually do the real molecular dynamic simulations. Here we can monitor different thermodynamic properties and also different structural quantities. Then in the end, what we can do is that we can make the final calculation of the thermodynamic and structural quantities which we have monitored during the production phase, and we can also do some estimates of the error using some statistical analysis. So these are the 5 different points that we need to consider when setting up and doing a real MD simulation here. So let's look here at the first part in a bit more detail here, namely how we represent the system. Here we can generally choose between an atomic level representation or a united atoms level of this system representation. We talked a little bit about it when we discussed molecular mechanics, and the meaning here is the same as in molecular mechanics. In the atomic level representation, what we do is that we represent all atoms explicitly in the simulation, and in the united atom representation what we do is that we truncate, for example, the different chemical groups into some effective or some more, well, it's not functional groups in a chemical sense, but into some regions, and we can even coarse grain this even more here. So in all of these 3 drawings here, these settings here actually represent, well, the same molecule but at a different molecular detail. Of course, it is desirable here to do the simulation using the representation here at the left, that is at the atomic level, because here we will be able to get much more information, because this is a much more detailed representation of the system. But it is also more expensive. We need to calculate more interactions because we have more atoms available. So if we want a maybe faster MD simulation without that much detail, then we can coarse grain the simulation and we can treat the system in this way here. So pay attention to which kind of information you actually want to achieve from the MD simulation, and then choose the system representation in accordance with what you actually want from your MD simulation. We also need to discuss a little bit on the time step here, because it is very crucial to choose a correct or at least a physically correct time step in the MD simulation here. Now the time step size is generally determined by the fastest process in the system. If we choose the time step which is to be too small, then as illustrated here, the simulation will take very long, and well, we cannot actually obtain much physical information from the simulation, simply because we need to run a very long simulation in order to really get the atoms move. Also, it can be subject to round off errors. If we choose the time step to be too large here, then we can actually introduce some physical artifacts. For example, this picture here illustrates that if we start out here at t equal 0, for example, then if the time step is too large, then we can actually predict here that these two atoms here are allowed to cross each other, because we don't know in detail what is happening between this point here and that point here. We only know in detail what is happening at this point and this point here. So it's really all about choosing a time step which is not too small, but which is not too large either. As I said before here, the time step is generally determined by the fastest motion in the system, and usually the stretches of the XH bonds, these represents very fast motions, for example the CH bonds and so. But usually we do not have any significance of those in our simulation. So for example, if we are to study a protein folding, then we really don't care about the motion or the detailed motion of the CH stretches here. So in such cases, it is convenient to freeze the CH stretches in the system, for example, using the shake algorithm here. So what we do is that we constrain the bond lengths to the equilibrium during the simulation, meaning that we effectively freeze out this motion so that we can use a larger time step in our simulation. This means that we can simulate the system at the same cost, but for a longer time. When do we actually have this equilibrium that I talked about here as an important thing in the setup of the simulation? Well, it can actually be quite difficult to answer this question here. But one indicator of an equilibrium in our system is by looking, for example, at the energy, the temperature, the pressure, the volume or the density, and then to monitor when these curves tend to begin to flat out, so to say. As an example here, we can look here at the potential energy here. As we can see here, a lot happens here in the very first part of the simulation, from around 2 to 8 picoseconds and so on. And then the energy here begins now to flatten out here. So by this we would say that after around 8 picoseconds or so in the system, we have actually reached the equilibration phase in our system. Until or before the 8 picoseconds have been reached, a lot of structural things happens in our system due to the fact that we are now in the heating up phase. So we don't have a very good representation of our real system. So when we are to actually look at the production phase, well, then in this case here, the production phase should begin, let's say, after 8 picoseconds and so on. You can also look at the temperature, the pressure, the volume and the density, and they should all show kind of similar curves here, that is a flattering of these quantities here at the time where we have actually reached the equilibrium. So the last stage here that we are to do in the MD simulation, this is the production run and the result analysis. So after the system now has reached this equilibrium, we continue the MD run, and here we collect configurations that we extract from the trajectories and we save them for further analysis. After this, we can view the trajectories, that is, we can view the trajectories as a movie, and we can use these trajectories in order to calculate thermodynamical and structural quantities such as heat capacities, densities in our system, radial distribution functions, which gives us information about how things are actually distributed, masses distributed in our system. We can do calculation of vibrational spectra and so on. In the exercises, we will be looking more into calculation of some of these properties here. So let's end this short introduction to molecular dynamics here by actually viewing a short movie here. This movie here shows a protein, and then we have a carbohydrate outside this protein, and what we simulate here is how this carbohydrate actually enters into the protein and how it actually binds here to the protein. So all of this can be studied using the great concept of molecular dynamics.